Hello, welcome. This is Physics 104A homework solutions for Chapter 10 on rotational motion. We start with number 11. Determine the angular speed in radians per second of Earth about its axis, the minute hand of a clock, the hour hand of a clock, and an egg beater turning at 300 RPM. All right, we'll start with A, Earth about its axis. So we want to get this in radians per second. And let's think about the spin of the Earth. It spins one full rotation, so 2 pi radians in a day. So we can start the frequency by saying that it's 2 pi radians per day. And let's turn that to radians per second. So a day is 86,400 seconds, and we get 7.27 times 10 to the negative 5 radians per second. Part B, the minute hand of a clock, and we think, well, the minute hand goes 2 pi radians in 1 hour, and let's do 1 hour over 3,600 seconds, so we get 1.75 times 10 to the negative 3 radians per second. The next one is the hour hand of a clock. So the hour hand goes around a full rotation, or 2 pi radians, in 12 hours. Do the conversion to seconds, and we get 1.45 times 10 to the negative 4 radians per second. And finally, an egg beater going at 300 revolutions per minute. And so we'll turn revolutions into radians by 2 pi radians over 1 revolution. Turn those minutes into seconds, 1 minute over 60 seconds. And we get 10 pi radians per second, which comes out to be 31.4 radians per second. Number 15, a compact disc's rotation varies from about 200 RPM to 500 RPM. If the disc plays for 74 minutes, what is the average angular acceleration in RPM per second? So revolutions per minute per second and radians per second squared. It's a kinematic problem. We have omega naught of 200 RPM, omega 1 of 500 RPM, and time of 74 minutes. Because the first question asks us about RPM, it's best not to convert it yet to radians. So we'll say that the average angular acceleration is the change in omega over change in time. So 500 to 200, so 500 RPM minus 200 RPM, divided by 74 minutes, which is 4,440 seconds, and we get 0.068 RPM per second. And then let's turn that to radians per second squared. So let's write it this way, 0.06, I've taken it out instead of rounding it off, 0.06757 revolutions per minute second. That's the answer we got up top. And let's convert all those units. So we need to turn those revolutions into radians. We need to turn one of those powers of minutes into seconds. So let's get rid of revolutions first. 2 pi radians over a revolution. Let's now get rid of those minutes on the bottom, 1 minute over 60 seconds, and we get an answer of 0.0071 radians per second squared. Number 16, during startup, a power plant's turbine accelerates from rest at 0.52 radians per second squared. How long does it take to reach its 3,600 RPM operating speed? And how many revolutions does it make during this time? Let's start with the given information. Omega naught is 0. Acceleration is 0.52 radians per second squared. Omega 1, it gives it to us as 3,600 revolutions per minute. But let's turn that to radians per second. So 376.99 radians per second. And now, given this information and that it's asking for time, we're going to go to this kinematic equation, omega 1 equals omega naught plus alpha t. We're going to solve for t, so it's omega 1 over alpha. And we can plug in those values. Radians per second is omega 1 divided by alpha is radians per second squared. So we'll get an answer of 725 seconds. More precisely, 724.98. We might have to use that later, but I'll round it to 725 seconds, which is about 12 minutes. Question B is asking how many revolutions does it make during this time? And so without doing too much math, we think it's going to be getting up to 3,600 revolutions per minute. Every minute, thousands of revolutions is what it'll eventually get up to. And it's running for 12 minutes, so we expect it's going to be many thousands of revolutions. Well, let's use this equation that the final omega squared is the initial omega squared, which was 0, plus 2 times alpha times delta theta. Let's solve for delta theta, as you can see here, and I get 136,655 radians. It's asking how many revolutions, so we'll divide by 2 pi and get about 22,000 revolutions. Also, you could have used, you can see here in the green, this equation, theta equals theta naught, which is 0, omega naught t, which is 0, plus 1/2 alpha t squared. And you should also get the same answer of about 22,000 revolutions. Number 20. A car tune-up manual calls for tightening the spark plugs to a torque of 35 Newton meters. To achieve this torque, with what force must you pull on the end of a 24 centimeter long wrench if you pull, part A, at a right angle to the wrench shaft, and B, at 110 degrees to the wrench shaft? All right, drawn a little picture here. Part A is pulling perpendicularly, part B is at a 110 degree angle. We have torque, we have the lever arm, and we want to know the force. So let's use this equation that torque equals force times lever arm times sine theta. Solve it for force equals torque over lever arm times sine theta. And then we just plug in the values, as you can see here. For part A, with the 90 degree angle, we get 146 newtons. For part B, at a 110 degree angle, we get 155 newtons. Notice this is asking how much force do you need to supply. So because in part B, it's not the best angle, you're going to lose torque. And so you have to compensate by putting more force into it. But certainly you can minimize the force you need to exert by pushing at a 90 degree angle. Number 23. 4 equal masses M are located at the corners of a square of side L connected by essentially massless rods. Find the rotational inertia of the system about an axis A that coincides with one side and B that bisects two opposite sides. All right, we've got to draw a picture here. Here are the 4 masses, and part A says that the axis of rotation coincides with, as you can see in the picture, one side of the square. The moment of inertia of the system is going to be the moments of inertia of all 4 of the masses. And so let's start to the upper left, and I'll go clockwise around. This mass is being rotated with a lever or a radius of L, the length of the square, and so it's going to contribute ml squared. This next mass, upper right, does the same, ml squared. The 2 masses on the bottom have an r equal to 0. They contribute nothing to the moment of inertia. And so ml squared plus ml squared, and we get 2ml squared. Now part B says let's have the axis go, as you can see in my picture right here. The axis bisects the 2 opposite sides, just like this. Okay, so let's take, coming from the upper left mass right there, its contribution to moment of inertia is mass times, and its distance from the axis is L over 2, so L over 2 squared. So we have m times L over 2 squared. And then you see that every mass contributes the same amount. They're all a distance of L over 2, and so it's going to be m times L over 2 squared times 4. And when you work that out, you should get ml squared. Number 25. The chamber of a rock tumbling machine is a hollow cylinder with mass 120 grams and radius 8.5 centimeters. The chamber is closed by end caps in the form of uniform circular discs, each of mass 33 grams. Find the rotational inertia of the chamber about its central axis and the torque needed to give the chamber an angular acceleration of 3.3 radians per second squared. All right, we have a picture here. We have a hollow cylinder, and we've got two discs, and I've drawn with a dotted line the axis of rotation. So let's first consider the hollow cylinder. It's got a moment of inertia. We can look it up in the table in the book, but of its mass times r squared. So I've used big M for its mass, and then big R is its radius, so mr squared. Then we think about the moment of inertia of the two end caps, the discs, and the moment of inertia of a disc is 1/2 mr squared. So here I've used 1/2 little m times r squared, so the discs have a different mass from the cylinder, but they do have the same radius, so I'm using the same capital R for radius. So for a disk, it's 1/2 mr squared, but there's two of them. So 2 times 1/2, and that becomes little mr squared. And so the total moment of inertia, I've factored out the r squared. It's big M plus little m times r squared. And then we fill in the given values. Now the values given in the book were in grams and centimeters. Let's keep it all in MKS units, so kilograms and meters. And you should get 1.1 times 10 to the negative 3 kilograms meters squared. Once you know that, finding torque is easy. It's giving the alpha, so torque equals I times alpha. So moment of inertia times the acceleration, and you should get a torque of 3.6 times 10 to the negative 3 Newton meters. Number 30. A 25 centimeter diameter circular blade has mass of 0.85 kilograms. Distributed uniformly in a disc. Part A, what is its rotational kinetic energy at 3,500 RPM? And part B, what average power must be applied to bring the blade from rest to 3,500 RPM in 3.2 seconds? All right, I have the given information in meters and kilograms. It's a solid disc. And so I've also converted 3,500 RPM to radians per second, so 366.519 radians per second. The kinetic energy is 1/2 I omega squared. So we have the 1/2. If it's a disk, that's 1/2 times mass times radius squared, and then times omega squared. And we need to use all MKS units so that this comes out to be joules. And I get 446 joules. Now the power, it says, what is the average power that needs to be applied to bring the blade from rest to that speed in 3.2 seconds? And so we can think that power is work over time. By the work energy theorem, work is change in kinetic energy. And change in kinetic energy in this case is the final kinetic energy minus zero because it started at rest. So the final kinetic energy is what we answered for part A, 446 joules. And we have to do that in 3.2 seconds, so we get 139 watts. Number 32 asks about a baseball with the given information. It asks what fraction of its kinetic energy is rotational. And what we're going to do is we're going to compare the translational kinetic energy with the rotational kinetic energy. Here I have all the given information. It's important here to note that for a solid sphere, the moment of inertia is 2/5 mass times radius squared. The translational kinetic energy is 1/2 mv squared. So we plug in all the given values, we get 81.675 joules. The rotational kinetic energy is 1/2 I omega squared. And we're going to substitute in for I, 2/5 mr squared, plug in all those values, and you get 0.0724 joules. When you add up those kinetic energies, you get 81.747 joules. The question asks what fraction of its total kinetic energy is rotational. So let's set up a ratio here. The kinetic energy rotational over kinetic energy total. So we divide these two numbers. It's going to be very small, 8.86 times 10 to the negative 4. And if we want to give that as a percent, that's 0.089%. Number 37. This is based on example 10.5. It says, find the rotational inertia of a meter stick with mass 172 grams about a perpendicular axis through its center. Treat the stick as a thin rod. Part B, the meter stick's width is 2.54 centimeters. You can treat the stick more accurately as a flat plane. If you do so, by what percentage is your answer to part A in error? All right, so for a thin rod rotated about its center, moment of inertia is 1/12 ml squared. You can plug in those values. Make sure you do the mass in kilograms. You get 0.0143 repeating kilograms meters squared. And then it said, now treat it as a flat plane. So you can see the picture I have here. It has a little bit of a width A and a length B, and the length B is 1 meter and the width A is 0.0254 meters. And so moment of inertia for the flat plane is 1/12 m times a squared plus b squared. A little bit of Pythagorean theorem going on there across the face of the ruler. And when you plug in those values, you get 1/12 m times 1.0006447. Now, I write that out, and I've underlined it because notice how that's a bit different from up here when we did 1/12 the mass times 1 meter. And so that shows the little bit of difference given by the little width of the ruler. Instead of 1, that's going to be 1.0006447. And so we get an answer of 0.0143426 kilograms meters squared. Very, very close to what we got in part A. Well, the question then asks, by what percentage is your answer to part A in error? So part B is going to be the more accurate answer. And so we have our estimate from part A minus the true value for part B divided by the true value from part B, and we get 6.4 times 10 to the negative 4, or 0.064%. Number 49, an example from microbiology. Full circle rotation is common in mechanical systems, but less evident in biology. Yet many single-celled organisms are propelled by spinning tail-like flagella. The flagellum of the bacterium E. coli spins at some 600 radians per second, propelling the bacterium at speeds around 25 micrometers per second. How many revolutions does E. coli's flagellum make as the bacterium crosses a microscope's field of view, which is 150 micrometers wide? All right, so the thing is moving. It's being propelled 25 micrometers per second, and the field of view is 150 micrometers. Let's figure out how much time is given here that we get to watch it. And so distance is speed times time. Time is distance over speed, so we get 6 seconds. So it's going to be in the field of view for 6 seconds. Now, the question is asking, in those 6 seconds, how many revolutions does the flagellum make? And we are given that it turns at about 600 radians per second. So omega is theta divided by t, and therefore theta is omega t. You could have also gotten this from the kinematic equation that theta is theta naught, which goes to 0, plus omega naught t plus 1/2 acceleration times t squared, and that part goes to 0, and we're left just with the middle term of omega times t. So we have 3,600 radians when we plug in those values, 6 seconds at 600 radians per second, so 3,600 radians, and we'll divide by 2 pi and get about 570 revolutions. Number 52. A uniform rectangular flat plane has mass m and dimensions a and b. Use the parallel axis theorem in conjunction with table 10.2 to show that its rotational inertia about the side of length b is 1/3 ma squared. Okay, the table gives us the rotational inertia as it's rotated about its center of mass, right there. And the question is asking to find rotational inertia as it's rotated about the end point, or the edge right there. So moment of inertia using the parallel axis theorem is moment of inertia through the center of mass plus mass times distance squared. And distance in this formula is the distance between the center of mass axis and the axis that we're trying to figure out. So in this case, that's going to be A over 2. So we have 1/12 ma squared, that's given in the table, plus mass times the distance, which is A over 2 squared. And you can work through that as I've done here and see that it's 1/3 ma squared. And it's actually similar to a rod. So imagine that if we take B and we squish it down very short, because B isn't relevant here, it becomes a rod rotating about its endpoint, which would be 1/3 mass times length squared. Number 53, back to the flagellum of E. coli. It exerts a typical torque of 400 piconewton nanometers. So instead of newton meters, it's giving piconewton nanometers on the flagellum. If this torque results from a force applied tangentially to the outside of the 12 nanometer radius flagellum, what is the magnitude of that force? All right, we're given torque, we're given the lever arm, what is force? And so we can use this equation, torque equals force times lever arm. It's applied tangentially, so that's going to be sine of 90 degrees, which is 1. That's why I haven't even written the sine theta here. And force is torque divided by lever arm, so 400 piconewton nanometers over 12 nanometers. Conveniently, it's the same nanometers and nanometers. Those will divide out, and we're left with 33 piconewtons. Number 54, verify by direct integration Table 2's entry for the rotational inertia of a flat plane about a central axis. All right. To find moment of inertia, well, first let's draw a picture. We have a flat plane about the central axis, and I've called the length that's parallel to the axis B and the width of it A, so it's going to correspond to the table that's given in the book. Moment of inertia in general is the integral of r squared dm. I'm going to divide the flat plane into many thin rectangles, these thin strips of width dx. And so the ratio of the areas of the strip divided by the plane. So if you look at that strip in green, it has a length of b and a width of dx, so its area is b dx, divided by the total area of the plane is a times b. And that equals the ratio of the masses. So the mass of the strip is dm over the total mass is big M. And you can see that the b's divide away, and I've got, solving for dm, that's mass divided by a times dx. And then we're going to take the moment of inertia integral at the top, and we'll evaluate it here. So we've got r squared, I'm calling that x squared because we're evaluating just in the x direction. dm, the line above, says it's m over a times dx. And so now we get to integrate over dx. Let's put our limits of integration, go back to the picture. We always make the axis of rotation 0. So the left limit is negative 1/2 a, and the right limit is 1/2 a. So here I have a over 2 and negative a over 2. And now we go through that integral. So take the constant m over a, put it out to the side of the integral, and we're integrating x squared dx. That becomes 1/3 x cubed. I put my 3 to the outside. And when you plug in those limits of integration, you should get, as I've gotten here, it eventually comes out to be 1/12 ma squared. And that is what's given in the table in the book. Number 55, a very robust problem, has many components to it. You're an astronaut in the first crew of a new space station. The station is shaped like a wheel. It gives the dimensions. When the crew arrives, it will be set rotating at a rate that requires an object at the rim to have radial acceleration of g, thereby simulating Earth's gravity. So when you arrive at the space station, it's not rotating. and you have to fire the rockets to get it rotating to a certain speed. This will be accomplished using 2 small rockets, each with 100 newtons thrust mounted on the station's rim. Your job is to determine how long to fire the rockets and the number of revolutions the station will make during the firing. All right, well, I've drawn a diagram here. We have a radius of 11 meters, and there's my little rockets firing. This one fires that way, that one fires that way tangentially. And it says there are 2 rockets with a force of 100 newtons each. So I'm just going to say they're working together, so you have 200 newtons of force total. Let's look at these different relationships. So acceleration, this is going to be the radial acceleration, is omega squared r. And that's the radial acceleration that you want to get up to 9.8 meters per second squared. So I relate it to the rotational speed, omega squared r. And let's solve for omega. So omega then becomes square root of a over r, which is square root of g over r, because you want to simulate Earth's gravity. So we plug in the square root of 9.8 meters per second squared over 11 meters, and we get an omega of 0.94388 radians per second. So that is the speed that we want to get the space station rotating at. We're going to accomplish that by firing 2 rockets, each of 100 newtons. So we're going to get 200 newtons of force. The torque that we're going to get is the force times the lever arm over which it's applied. It's on the rim, so a radius of 11 meters. And so we're going to get from the rockets 2,200 Newton meters of torque. Now, the moment of inertia of the space station, it says that the mass is essentially all along the rim. Unlike the picture I have, the painting down below has those spokes, but we're just going to assume that most of the mass is along the rim, because that's what the problem says. So moment of inertia is mr squared. It's a ring. And we plug in the mass times the radius of 11 meters squared. We get 6.05 times 10 to the 7th kilograms meters squared. Now we can figure out the acceleration, because we're going to use torque equals I times alpha, which means acceleration is torque over I, 3.636 times 10 to the negative 5 radians per second squared. And now that we know the acceleration, and we've already found out up at the top right here what the omega needs to be, now we just solve for time. So if alpha is change in omega over time, then time is change in omega over alpha, but it started from rest, so I'm just calling that change in omega, the final omega. And we plug in, we have final omega was 0.94388 radians per second. We have the acceleration that we solved for in the previous line, 3.636 times 10 to the negative 5 radians per second squared. And so we get 26,000 seconds, or about 7.2 hours. So we need to fire those rockets for 7.2 hours. And then finally, how many revolutions does it spin through? Let's use this equation, theta equals theta naught, which is 0, plus omega naught t, which is 0, plus 1/2 alpha t squared, and we get 12,250 radians, or 1950 revolutions. Number 62. A hollow ball rolls along a horizontal surface at 3.7 meters per second when it encounters an upward incline. If it rolls without slipping up the incline, what maximum height will it reach? And this is a lot like in a previous chapter when we had something maybe sliding along without friction and going up a hill, and we did that by conservation of energy. The only difference here is now we have to take into account in the kinetic energy that it is rolling. So here is a picture, E1 and E2, so energy at state 1 when it's at the bottom of the hill, energy at state 2 when it's at the top. It's gone up a height h, and h is what we want to solve for. So energy at state 1 is the total kinetic energy. It's got no potential energy, it's just all kinetic. And that is the rotational plus kinetic, or translational kinetic energy. So 1/2 I omega squared plus 1/2 mv squared. And on the right, for energy at state 2, it's all potential energy, mgh. And let's see what we can do with kinetic energy to clean this up. The I, because it's a hollow ball, is 2/3 mr squared. So it is 1/2 times 2/3 mr squared times omega squared, but r squared omega squared for a rolling body is v squared. So let's replace that r squared omega squared with v squared. You see the 1/2 times 2/3 becomes 1/3. So we have 1/3 times mass v squared plus 1/2 times mass v squared equals mass times gh. And so we can divide out the mass, and when we clean up the left-hand side, we get 1/3 v squared plus 1/2 v squared equals gh. We'll add the 1/3 plus 1/2 and it becomes 5/6. And let's divide both sides by g. So solving this for height, you should get 5v squared over 6g, and plug in the values that are given in the problem. It says it was going at 3.7 meters per second, and g, of course, is 9.8, so we get a height of 1.16 meters. And that is the end of the Chapter 10 homework. Have a great day.